Hello and welcome. In this video, we're going to be taking a look at the basic concepts of integration with multivariable functions. Now, if you remember when we started introducing the concept of the partial derivative, it's not like we had to completely reinvent all of the rules of derivatives. It was a matter of taking the derivative with respect to one variable at a time, treating the others as constants. Now, we have a fairly similar kind of process here for integrals as well. But what is the application of integrating a function of multiple variables? So let's start off with a function of two variables, and let's define something that we call the double integral of that function. Now here, I've got a function of two variables, and we can represent that as some kind of surface in 3-dimension. Now remember, if you go back to single variable calculus, the definite integral is over some kind of interval along the x-axis, a to b. Well here, since we have two variables, we're going to be taking a look at an interval along the x-axis, let's say from a to b, but also an interval along the y-axis, and let's say maybe from c to d. Instead of giving us just an interval then, the two intervals combined actually give us a rectangle on the xy plane. The boundaries of that rectangle are x equals a, x equals b, y equals c, and y equals d. And also this time around, instead of just looking for area under a curve, we're going to be looking at the region under a surface over a rectangle. That region has a volume. So this double integral that we're going to invent is a tool for finding the volume of that region. We could try to visualize that. These four corners of the rectangle, if we projected them up onto the surface, will give us four corners of some kind of patch on the surface. It's not exactly a rectangle, but it's more or less a box shape. We have a rectangle for the base, we have flat sides, and it's just a matter that we have a curved top. That might give us a little bit of an idea of how we can try to calculate that volume. Just like with the definite integral of a single variable function, where we took the interval and subdivided it into subintervals, in this case, we're going to divide that rectangle up into subrectangles. So in this case, R, we're going to divide that up into subrectangles that all have equal width and equal length. And this should be pretty familiar. We're going to be taking that range for x from a to b and dividing that up, let's say by some number m. That gives us a width, delta x. We'll do the same thing with y and take our region from c to d, subtract d minus c, and divide by n. You can notice here that we don't necessarily have to have the same number of divisions for x and y. Let's suppose we want to divide our x interval up into 5 subintervals, and we want to divide our y interval up into 6 subintervals. Well, then we'll end up with a grid pattern here. And each of these smaller little rectangles, maybe we could just denote each of those as being r sub ij, where I would be an index from 1 to 5 horizontally, and j would be an index from 1 to 6 vertically. In total, that means we have 30 subrectangles. All right, now that we've got that divided up, the first thing we'll need is that the area of each of those little subrectangles is given by delta x times delta y. And let's just call that delta A. It's not the full area of the rectangle R. Delta A is just the little area of each of these subrectangles, R sub ij. Now, to get the actual volume of the whole region, we're going to start looking for the height of the function in each of those 30 separate subrectangles. Once we have the area of the base and the height of each rectangle, we can approximate the volume by adding up the volume of each of these smaller boxes. To get the height, we're going to pick a point in each of these little subrectangles. Here I've chosen the midpoint, but I could choose any of the 4 corners, or literally any point inside each of those subrectangles, just to get an approximation. Since there are 30 subrectangles, I'm going to need 30 sample points. We'll denote those sample points with xij star, yij star. That's the sample point in subrectangle rij. We can take that point and evaluate the function at the point to get the height of each of those little boxes. Now we just need to sum up the volume of each of those boxes, area times height, and let m and n go to infinity to get a better and better approximation. All of that put together gives us the actual definition of what we call a double integral of this function f over that region R. And so the definition here of the double integral of f over the rectangle R is denoted as this double integral, basically just two integral symbols with a little r to denote our definite integral over that region R of the function f with respect to area is equal to the limit as m and n go to infinity, and we need two summations here. One sum from left to right, I equals 1 all the way up to 5, or m in general, and another sum for the index j from 1 up to 6, or n in general, and that is going to be the sum of the volume of every subrectangle. Height, f of the sample point, x star, y star, multiplied by delta a, which equals delta x times delta y, given by these formulas at the top of the screen there. That's just the base area of each of those subrectangles. Now, just like in single variable calculus, this is called a Riemann sum. And we're just taking the limit as m and n go to infinity of that Riemann sum. If you remember from single variable calculus, working with Riemann sums and midpoints, for instance, is a bit of a tedious calculation. And it gets even worse here. If we choose m to equal 5 and n to equal 6, that's 30 sample points immediately. And 5 and 6 aren't really that big. This might not give you a very good approximation anyways. So what we really need here is a process, kind of like the fundamental theorem of calculus. How do we use what we've learned already from single variable calculus in order to evaluate this double integral? Well, that's this next theorem that's going to be vitally important so that we can get away without calculating Riemann sums. The theorem that makes all the difference here is called Buenis Theorem. And so long as we have a continuous function f of xy over that rectangle, and here's a couple different notations for our rectangle. We can use set notation, the set of all points x, y, such that x is between a and b and y is between c and d, or we can use notation with a Cartesian product. The integral a to b would be for x, the interval c to d would be for y. Buenis theorem says, as long as we have that condition, then the double integral of the function f of x, y, dA, again, that's called our double integral, can be written as two separate integrals. One integral, a to b, and you can see another integral, c to d. Now, the order of integration here is going to be in the order of these two differentials. dy, integrating from y equals c to y equals d, and then integrating with respect to x from x equals a to b. If we want to, we can actually change the order around. We can integrate first with respect to x from x equals a to x equals b, and then integrate with respect to y for y equals c to y equals d. Now, these two integrals here, dy dx and dx dy, are called iterated integrals. And really, they're nothing more than two separate single variable integrals that we're familiar with already from single variable calculus. The only thing to remember is that when you're doing an iterated integral, we are integrating with respect to one variable at a time, and we're holding the other variable fixed, treating it like a constant. For example, if we are iterating this integral with respect to y first and integrating from y equals c to y equals d, we integrate with respect to y and leave x just like constants, or constant multiples that are involved in the expression. And then, since this is a definite integral for y, we plug those numbers in. That means we should get a numerical expression, but potentially still involving x as a variable. That will give us a single variable function gx. That means if we have a particular iterated integral in the form of dy dx, then our first step is going to be looking for an antiderivative with respect to y. Let's call that capital F of x, y. Now, this antiderivative here is with respect to y, so that means that the partial derivative of capital F with respect to y should equal our original integrand, little f of xy. Now, we still need to evaluate from y equals c to y equals d. And when we do that, we shouldn't have any y's left in our expression anymore. At this point in time, we'll just have a function of one variable. Maybe we could call that g of x. G of x is really just capital F of x, b minus capital F evaluated at x, a by the fundamental theorem of calculus that we learned with single variable calculus. And speaking of single variable calculus, that's all we have now. A single variable definite integral for x equals a to x equals b. So again, we're going to be looking for an antiderivative. Let's call that capital G of x. G prime of x must equal little g of x, which is our current integrand. Now we're going to evaluate, since this is a definite integral, from x equals a to x equals b. And that will get us simply just a number. That value is the value capital G of b minus capital G of a through another application of the fundamental theorem of calculus. So the overarching theme here, if you haven't quite picked up the concept yet, is that the double integral is a new operation that only ends up being used when we have a couple variables, let's say x and y. But it's not really that new because what we end up doing is just some stuff that we learned from single variable calculus. We just integrate with respect to one variable at a time. Now keep in mind, this is with a rectangle and the boundaries are just going to be constants. That's not always going to be that easy, but for now, let's try an example so you can get a sense of how to just tackle iterated integrals in general. Let's evaluate a double integral of the function 4x cubed y with respect to a over the region R. And I'm using this notation where R is equal to square brackets 1, 5 cross square brackets 0, 3. In that order, that should be x from 1 to 5 and y from 0 to 3. Feel free to use set notation if you prefer that. Now let's try setting this up in the two iterations, dy dx and dx dy. dy dx, we have to make sure we have our integrals in the correct order. The outer integral goes last with respect to x from 1 to 5. The inner integral is with respect to y first from 0 to 3. If we want to change to dx dy, then the inner integral has to be from 1 to 5 and the outer integral has to be from 0 to 3. And by Buenis Theorem, we should get the same result no matter which of these two methods we choose. So let's start off with this first one on the left. 4x cubed y, and we're integrating with respect to y. Well, 4x cubed can be treated as a constant, and we just need to find the antiderivative of y. Well, that's y squared by 2. Now, you can see that this is just a regular single integral at this point in time, so maybe before we evaluate at y equals 0 and 3, we can simplify 4 over 2 to get 2 and move that 2 outside of the remaining integral. Then simply evaluating at y equals 3, we're going to get 9x cubed, and evaluating at y equals 0, luckily we just get 0. Now we should be fairly comfortable at this point in time with single variable integrals. We can move the 9 out front. 2 times 9 will give us 18, and then we'll just need to look for an antiderivative of x cubed, which would be 1/4 x to the 4. We'll evaluate 1/4 x to the 4 from x equals 1 to x equals 5. And we can even reduce this 18 over 4 while we're at it. Reducing that to 9 over 2, we have 5 to the power 4, 625, minus 1 to the power 4, which is just 1. Now that is 9 times 624 divided by 2. That gives us 2,808. And let's not forget that if you want to imagine what that means geometrically, you'd have to kind of know what this surface looks like. Z equals 4x cubed y. But if we took that surface and looked at the volume underneath that over this rectangle, this would be that volume, 2,808 cubic units of volume. Now let's try the other order and we should get the same result. But the first step is going to be quite different. We're going to be looking for an antiderivative of 4x cubed y with respect to x. Now y is just constant, so you just need to look at the antiderivative of x cubed. Now that would be x to the 4 over 4. But we actually have a 4 there right now. You can see that the antiderivative of 4x cubed is literally just x to the 4. And that might be a little easier then. Treating y as a constant, our antiderivative is x to the 4 y. You can always double check by taking the partial derivative of that expression with respect to x and see that we do get 4x cubed y. Now this is a definite integral from 1 to 5, so we're going to have to evaluate from x equals 1 to x equals 5. That's going to get us 625 minus 1 all times y. Now, we've seen this before, 625 minus 1. Well, that's 624, and that can even just be moved out front right away. And at this point in time, hopefully you can see that we are slowly getting our way to the exact same answer. Now we have a single variable problem. We need the antiderivative of y, which is 1/2 y squared, and evaluate from 0 to 3. And that gives us 9 over 2 again. And we already know what 9 over 2 times 624 is. That is 2,808. That's definitely not a proof of Buenis theorem. It's just a way to confirm that yes, it does actually work in this particular example. We're going to omit the proof in this video, but you can imagine that it is vitally important because it is that link between turning double integrals into iterated integrals, which allows us to use all of our concepts from single variable calculus. Now I have one other shortcut that I want to show you in this video, but I think it always helps to try to visualize what this double integral means in terms of its Riemann sums. Since that's a bit of a nuisance, let's go ahead and take a look over at Maple. This student multivariate calculus package has a lot of commands in it. And if I remove this full colon from the end of that line and hit enter, you can just see how many commands are included in Maple 2021 version. And there is an approximate int command. Maybe you've seen that before, but this approximate int command is actually a version that works with double integrals. So I will run that with the full colon at the end and just hide the output. Here's the approximate int command and our function for x cubed y from x equals 1 to 5 and y equals 0 to 3. And I'm choosing the option output equals plot. So let's see what we get there. Maybe I'll zoom this in a little bit here. And the default method seems to be midpoint Riemann sums. You can even see that iterated integral. The actual value Maple confirms is 2,808. This is a 5 by 5 grid with midpoints, and we get an approximation 2,773.4. But you know what? Isn't really that bad. But more so, here's the actual representation. You can see the grid at the bottom there. That's our rectangle, 1 to 5 and 0 to 3 for y, divided up into a 5 by 5 grid. And each of those are just boxes. Now you notice it's actually a square, but if it wasn't a 5 by 5 grid, each of the bases would just be a rectangle. And if you take any of these rectangles, we're going to plug the midpoint into the function and determine the height. So you should see that the midpoint of the top square of each of these boxes is passing right through the surface. So this is what that double integral is actually doing for us. As m and n go to infinity, this approximation ends up equaling the proper volume underneath that. All right, now before we end this video, I do want to show you one other very useful shortcut to remember for the future for just rectangular regions and very nice functions. But don't worry, this is actually going to be a useful shortcut that shows up frequently, so it is worthwhile to show you right now. If we have a rectangular region, which for right now, that's all we've really had to deal with, and we have a function that is factorable, and this is this new key ingredient, f of xy can be written as some factor involving only the x variable and some factor only involving the y variable. That particular separable kind of function. Then if we have the integral dy dx, where let's say x goes from a to b or y goes from c to d, by Buenis theorem, we could also even write that in the opposite order. What we can do is pretty clever here. Why don't we take a look at this first iteration and see how this shortcut arises. If we're integrating with respect to y first, then we're treating x as constants. And this whole factor, g of x, is treated as a constant. Now that constant multiple can be moved out front of the first iterated integral. It's from c to d for y. We're going to hold on to that for a moment, and we'll integrate with respect to y. But this is a definite integral for y. So once we finish integrating with respect to y and plugging in those values, we get a numerical expression. And that numerical expression would then be a constant multiple for the next integral with respect to x. since that's going to be a constant multiple, it can also get moved out. And in the end, all we've really done are two definite integrals, one for y and one for x. We've done them separately, and we multiply their results. So the shortcut says, if we have this kind of function, then we can integrate the factor g of x for x equals a to x equals b, and integrate the factor h of y for y equals c to y equals d. Now, if we look back at this last example, that's exactly what we have. 4 is a constant multiple. That can either get attached in with the x cubed, or it can get thrown in with the y. But certainly we can separate this up into two separate factors, one for x and one for y. And because we have a rectangle, we can actually split this into two separate definite integrals and multiply the results. So why don't we try that strategy here? We already know how to write the double integral 4x cubed y dA in an iterated integral, but now let's take a look at separating the factors. 4x cubed with respect to x, x equals 1 to 5. We can tackle that on its own, and the other integral will be of just y with respect to y from y equals 0 to y equals 3. Now we're really just relying on single variable calculus. Nothing here is even treating other variables as constants anymore. Now that we've got these two separate variables, we can just find antiderivatives. The antiderivative of 4x cubed would be x to the 4, and the antiderivative of y would be 1/2 y squared. And we just need to evaluate from x equals 1 to 5 for that first definite integral, and y equals 0 to 3 for the other definite integral. We've done this before. 5 to the power 4 minus 5 to the power 1 is 624, and we have 1/2 9 squared minus 1/2 0. There's our 624 times 9 over 2 again, and we already know that that should give us 2,802. Now, the purpose of this video is just to get a little taste of double integrals, sticking to rectangular regions for now. But that's all about to change. We might want to take a look at the area under a function over a more interesting region. Depending on the shape of that region, those boundaries are not going to be just constants anymore. Not necessarily just interval a to b and interval c to d. But the good news is everything that we've just used here for rectangular regions is going to apply into more general regions. So stay tuned. Thanks for watching, and I'll see you in the next video.